Imagine being able to listen to the universe, not with your ears, but with instruments so sensitive they can catch the faintest ripple in the fabric of space itself. What secrets would those cosmic vibrations reveal? Especially when they come from two titanic black holes smashing together, events so powerful they shake the very structure of reality. This is the strange, mind-bending world of gravitational waves. Waves that travel not through air or water, but through space-time, and what they show us about the most extreme objects in existence: black holes. Let's start at the beginning. Over 100 years ago, Albert Einstein proposed something wild in his theory of general relativity. Mass and energy could curve space, and when massive objects like black holes move, they could create ripples, waves in the very geometry of the universe. But even Einstein doubted anyone could ever detect them, arguing the effect was just too faint. For decades, gravitational waves were more science fiction than science. Fast forward to 2015. After years of engineering and anticipation, the LIGO detectors in the United States picked up a signal. Not just any signal, but a chirp lasting a fraction of a second, matching exactly what physicists predicted would be the gravitational wave from two colliding black holes. For the first time, humanity had direct evidence that black holes, those invisible monsters, actually merge and send out a shout across the cosmos. So what do gravitational waves from black holes really tell us? First, they are direct evidence that black holes exist and can collide. For decades, black holes were weird solutions to equations, things we inferred but never saw directly. But gravitational waves are a handshake from the black holes themselves. Proof that something invisible, something entirely made of warped space-time, can make a sound in the universe. Second, these ripples reveal exactly how massive the black holes were and how far away they lay. Gravitational waves aren't just a faint blip. They carry a signature. By analyzing the frequency and amplitude of the signal, the chirp as it rises and then cuts off, physicists can rewind the merger, like running the universe in reverse. They can measure the masses of the black holes, how fast they spiraled around each other, and how much energy was blasted out as gravitational waves. In that very first detection, the two black holes were about 29 and 36 times the mass of our Sun, merging more than 1 billion light-years away, making the entire collision happen before dinosaurs ever walked the Earth, and finally reaching us in 2015. There's something almost poetic about this. It's like learning about a distant thunderstorm, not from the light or the rain, but from the faintest tremor that reaches your feet, telling you not just that it happened, but how big the storm was, how far away, and even what the clouds were doing. The universe speaks a language of vibration, and we're just beginning to listen. Reflecting on this, black holes themselves are silent, emitting no light, no radio signal, nothing that traditional telescopes can see. For centuries, astronomers could only observe their effects indirectly, stars orbiting invisible companions, or X-rays as matter falls in. But gravitational waves are a completely new window. They let us observe black holes directly, by the very shaking of the universe they cause. Now, let's explore deeper. What happens in those final moments before the black holes merge? As they spiral closer, they orbit each other thousands of times a second, moving at half the speed of light or more. This rapid motion warps space so violently that it emits a burst of energy, not as light, but as gravitational waves. But these waves aren't random. Their pattern encodes the last dance of the black holes, how fast they spin, how circular or elliptical their orbits were, And even if the two were tilted or aligned like cosmic gyroscopes gone wild. By catching these details, physicists get clues to how these black holes got together in the first place. Did they live together from birth? As two massive stars that died side by side? Or did they find each other in the chaos after being born separately, wandering through dense star clusters before finally becoming locked in a gravitational embrace? The shape and frequency of the gravitational wave reveals their history, like hearing the accents in someone's voice and guessing where they grew up. The story doesn't end at the collision. After impact, the merged black hole doesn't just sit quietly. It rings, like a bell struck by a hammer, vibrating with frequencies set by its new mass and spin. This ring-down phase encodes information about the final black hole's size, spin, even possibly whether it matches what Einstein's theory predicted. These details test general relativity in some of the strongest gravity ever seen. If the ring doesn't match the expected tone, it could hint at something beyond our current understanding. Maybe extra dimensions or new physics lurking just outside our grasp. In other words, gravitational waves don't just confirm what we know about black holes. They challenge the limits of our theories, pushing Einstein's equations to their breaking points. Now, consider energy. When two black holes combine, the resulting black hole weighs slightly less than the sum of the originals. Where did that missing mass go? It was converted, literally, into gravitational waves. In that first detection, about 3 solar masses just vanished from the universe, transformed into gravitational energy, and carried away at the speed of light, rippling outward across the cosmos. For a moment, the collision released more energy than all the stars in the universe combined, but in a form so subtle we only just learned to detect it. Let's pause and reflect on what that means. All our astronomy up to now has been based on photons, particles of light. But gravitational waves are a new messenger, a vibration of pure geometry. They aren't blocked by dust or gas, and they aren't absorbed or scattered by galaxies in between. In theory, they can carry information unaltered from one end of the universe to the other. Suddenly, cosmic events once completely hidden are now within our grasp. Let's turn to the strange poetry that humanity has always brought to the cosmos. For centuries, thinkers have imagined the music of the spheres, the idea that the heavens make a kind of cosmic harmony as they move. Pythagoras imagined planets and stars producing actual music, too faint for us to hear. Now, with gravitational waves, it's as if the universe really does sing, not in sound waves, but in space-time waves, playing a strange melody only the most sensitive ears on Earth can detect. One reflection comes to mind from the philosopher Heraclitus, who once wrote, "The unseen harmony is better than the seen." Gravitational waves prove this. The invisible universe is not silent. It's speaking a language we're just learning to translate. Think about this. Every detection to date has taught us something new. Some black holes are spinning astonishingly fast, while others appear to have been born from massive stars we didn't even know existed. We've seen colliding neutron stars, and those events not only send out gravitational waves, but also light and elements, creating gold and platinum in the universe. But with black holes, most of the time, we get only the gravitational sound and nothing else. It's like hearing footsteps in the dark, knowing something massive just passed by. Let's reflect for a moment on the scale of all this. The energetic waves detected by LIGO caused a distortion in space-time so small, it stretched and squeezed the detector's mirrors by less than 1,000th the width of a proton. That's the equivalent of measuring the distance to the nearest star, accurate to the width of a human hair. Yet from these tiny signals, entire stories of black holes, their masses, spins, even their dances before merging, unfold. Now, the future gets even more interesting. New detectors are coming online, like Virgo in Europe and Kegra in Japan, and soon, observatories in space, like LISA, will catch waves with longer wavelengths, revealing collisions of even more massive black holes, those millions of times the sun's mass at the centers of galaxies. Each jump in sensitivity is like turning up the volume on the universe, hearing fainter and more distant events, maybe even echoes from the very dawn of black holes themselves. Let's return to poetry for just a moment. One line from the poet Walt Whitman: "I hear the great spaces. My soul has measureless pride." That sense of cosmic awe, of hearing a universe bigger and older and stranger than any one lifetime, is precisely what gravitational waves bring to our science. They stretch human curiosity to its furthest edge. To sum up, gravitational waves teach us at least 8 astonishing things about colliding black holes. 1. They confirm black holes' existence, not as theory, but as cosmic players sending signals across the void. 2. They reveal the mass and distance of black holes through their unique vibrational signatures. 3. The pattern of the waves tells us about the story of the merger, their past lives, how they danced, and how they met. 4. The very nature and details of the ring down after collision helps us test the deepest laws of physics. 5. The energy released is staggeringly vast, converting mass directly into gravitational vibrations that traverse the universe. 6. Gravitational waves open a new, unblocked observational window, making even the darkest cosmic events visible, or rather audible, to science. 7. Every detection challenges our expectations, sometimes revealing black holes more massive, more distant, or with different spins than any seen before. 8. With each new wave, we push closer to understanding not just black holes, but the full symphony of the cosmos. From the earliest echoes after the Big Bang to the mysterious future fate of our universe. Standing here on this small blue planet, we have built instruments that let us feel the universe ripple and ring with cataclysmic events beyond imagination. We're not just observers, we're listeners, translating tremors in the very fabric of reality into stories about how the universe works. The ultimate question: what melodies, what revelations, what mysteries still lie hidden in the space-time between the stars? With each passing year and each new wave detected, we move closer to hearing the answer. The universe has begun to speak. Are we ready to listen?